What did I choose the recording as? Hey everyone, welcome to the July meeting of Tucson Amateur Astronomy Association's Astronomy Fundamentals Special Interest Group. That was kind of a mouthful. My name is Connor Justice. I am the group organizer most of the time, and unless you were here for us in June, I was out on vacation. This month, we're going to be doing something a little bit different than normal. We won't be having a constellation of the month, in part because I was running around because of the 4th of July holidays and a couple of other family things and forgot to make one and ran out of time. But also go through some of the main presentation a little bit more slowly than normal. The main topic this month, I'm going to actually be recapping and summarizing a series of really interesting research papers that have been published over the last 3 months in astronomy, touching on a variety of topics. Unfortunately, a lot of this is not going to have pictures because all the pictures were embedded in the research papers that were accessed behind a paywall. So even though some of this could be very much explained a lot better with graphics, I unfortunately don't have any. So I apologize for that. I will try to do my best to explain with words where I can. Going forward, we're actually getting close to ending the constellation of the months, having done all 88. I think we'll have all 88 constellations done by the end of the year, if not by January, which raises an interesting question of what if people want us to just circle back and start over constellations that have been done 5+ years ago, since we don't have archive presentations for many of them, or do we want to try to branch out into something else entirely and cover a different topic, a different recurring theme for one of our main presentations for some of our content? If you do have suggestions, please email them to the email account that sent out. Please excuse me for a second. I just got an email from someone who's trying to watch on Facebook, but I don't normally broadcast this on Facebook.
Right. It's a separate function to do Facebook.
Normally, right, but that's normally done on, I'm still, at the moment, I'm using my personal account because I need to circle back with Jim Dahl on something, and so this would be not, and I don't have Facebook set up at all on my local. I'm going to just forward her the meeting invite to Zoom.
Yeah.
If you will all give me a second while I take care of that, I'm going to pause the recording just because no one needs to stare at my email. Resume the recording and resume share. Resume share, please. Thank you. Having hit the button 5 times and it resumed at last. Okay, picking back up where we left off, while that little housekeeping task is done, I apologize. Is everyone able to see my screen again?
Yes, you're in notes mode, I think.
You should now be getting the slideshow.
There we go.
I was on my desktop still. I hadn't restarted the slideshow. So picking back up, since we did take a little breaker, this month we're going to be, if you do have suggestions and ideas for things that you would like to see once we finish the constellations, please email them to the email address that sent out the invite for the meeting, just so it's easier to keep track of for me. And if you do have questions on some of this, please let me know. I do occasionally get a little bit into things and talk a little bit too quickly. If I am going too fast, please just let me know and I will slow down. Or if you do have questions about something in particular, as we go through the slides, please just go ahead and ask. So as I had mentioned earlier, this month we're going to be talking about some recently announced research papers that were have been covered in some of the science press here in the last couple of months. For starters, we'll be talking about a recent study trying to figure out through a couple of interesting some data from Keck, one of the Hawaiian telescopes, not the Keck Observatory. What are the likelihood that the clouds on Venus actually can support life? And like this is microbial type life. A follow-up to that is a research paper that came from the SETI Institute, which was trying to get an idea for the question, as we are searching for exoplanets, how many planets and stars around us can perform these same type of searches that we are, if they had the technology to do so. Continuing on with answering a question of why are Jupiter and Saturn so hot in their atmospheres, which is interesting. A new supernova subtype has also been observed since it was first theoretically proposed over 40 years ago. And finishing it off with a talk about how magnetism can impact planetary formation around stars. So
a lot of physics.
The physics, there's not going to be a lot of talk with math in this. I typically keep that to a minimum unless it's absolutely necessary. So it's really just going to be a lot of science concepts. So hopefully there's not going to be anything here that's going to go over people's heads too much. So starting off with the likelihood of life in the Venusian clouds. So in 2019 and 2020, there was a study that published results that the chemical phosphine was detected in Venus's upper atmosphere. It is typically a compound that is not produced naturally. At least here on Earth, it's usually the result of chemical reactions by life producing things that they might need to sustain or do or power their own life cycles and cell division. The presence of this was used as a marker for a sign that life may exist in the upper atmospheric layer, the upper cloud layers of Venus, far enough away from the hellish surface of the planet, where on the ground it's 800 degrees Celsius and rains molten lead. So in June 21, last month, a follow-up study was released to that initial paper, which was trying to answer the question, how habitable the cloud layers actually are. Knowing that which I found kind of surprising, knowing that, we've known Venus has had a lot of cloud layers, and there's been a lot of speculation whether or not they could support life over the last 40 years since, I think, what was it, the Pioneer probes that went to Venus? And a couple of other follow-up studies since then that probes have made it to the planet, that there hadn't really been a paper that had analyzed this. So that was kind of interesting to see. In addition, on Earth, life forms are often found living in places where you wouldn't really expect them to be. These are referred to as extremophile life forms. Examples of these are worms found growing around volcanic events on the ocean floor. There are also signs of bacterial life living inside of boiling water found in volcanic hot springs. So really hot places really devoid of light, and a natural energy source, where it's just really, where, if we tried to live there, we'd probably, be saying, I want to go home and sit in my air conditioning while, within 5 minutes. So the primary interest in analyzing Venus's atmosphere is that, we would expect, if there is life at all, then it would be a form of extremophile, whether it's a heat tolerant or uses different chemicals as an energy source. I think, for example, going back to the volcanic vents example, the worms that live around hydrothermal vents on the ocean floor actually feed off of sulfur as an energy source. And since Venus's atmosphere is mostly comprised of sulfur, we know that, in theory, something might live in the clouds. But we do know, even though they are composed of sulfur, there's actually very, very little water in the clouds. But how much, though, is kind of one of those, well, it depends. And now this paper was analyzing data from a couple of other telescopes. Unfortunately, the paper didn't say, so I can't really say, was this Hubble data? Was this off of something from the Very Large Array over in Chile, or was this off of a Hawaiian telescope like the Subaru and so on? So I can't really tell you what telescope it was, unfortunately. But they did use those measurements and observations from these telescopes to try to calculate how much water and sulfur, what the concentrations of water and sulfur in the Venusian clouds is. So sadly, the signs for this weren't really all that great. Their math was coming out that the clouds in Venus contain 100 times less water than even the most drought-tolerant extremophiles on Earth are known to live in. So, not a lot of water there to power a lot of the chemical reactions that we typically associate with life. They also found that because there's so little sulfur, that the clouds generally consist of 78 to 100% pure sulfur in gaseous form. So, if you've ever, worried about having sulfur acid burns, if you like to mess around with chemistry in your kitchen for any reason at all, this is a lot higher than what you would get with sulfuric acid. Quoting something from the authors, they are saying that they said that sulfuric acid dehydrates cellular systems, and this removes water from the molecules that they use, and reduces hydrophobic interactions, which are reactions in cells that require water. And it also damages the cells themselves. So having high sulfur concentrations having sulfur concentrations as high as they are in the clouds is unfortunately not a good sign that the clouds may contain microbial life, which, again, hard to say for certainty, because it's been a long time since we've been to the clouds and we haven't actually sampled the cloud layers ourselves. But nonetheless, it's an interesting but unfortunate result. Any questions before we move on to the next topic? Okay. Moving on, the follow-up to this is a paper from the SETI Institute, which, for those not familiar with the acronym, this is the Search for Extraterrestrial Intelligence. This is a group that primarily uses radio telescopes to scan, looking for signals of we hope to be advanced intelligent life. As part of this search, and more generally, we have two primary means of detecting planets around stars other than our own. These are known as the transit method and the radial velocity method. The transit method, which is what has been used by the Kepler Space Telescope and more recently the TESS Space Telescope, these has these telescopes watching vast regions of space and observing all of the stars in that region for changes in brightness of the star that occur in a repeating pattern, and using these repeating dips in brightness as an indicator that a planet, it could be a large planet, it could be a very small planet. We've detected planets much smaller than Earth around other stars at this point. That a planet is actually passing in front of the star between us and the star that the telescopes are observing. So if you kind of imagine for a second that there's just a disk between a random star in the sky and us, kind of like that a planet is moving across that disk. It may not necessarily, orientation in space is weird. Things, one of the hardest things that's kind of to wrap your head around is that things in space aren't oriented in the same direction to each other. So, for example, some planetary stars will have their solar systems appearing as though they are face on to us. Others will have their solar systems oriented as though they are edge on. The transit method is more biased to detecting planets that are edge on, so that their planets are spinning around in the direction to us, rather than like we're looking down at a plate, if that kind of makes sense for people. The other method we have is called the radial velocity method. Here, what we do is we watch stars to see if they are wobbling in response to the gravitational tug of planets that orbit the star itself. And I apologize for the 2 typos in this slide. You can think of this as basically watching stars for tidal effects, like similar to how the moon, as the moon orbits the Earth, it pulls on our oceans to create tides. Well, similarly, all planets, as they orbit their parent star, have a similar effect. It can actually shift the position of the star and cause it to wobble very slightly. As you can imagine, this is something that's really, really hard to see. So the majority of our planetary detections to date have been done using the transit method. The radial velocity method is also geared toward planets that are much closer to us, because it is easier to detect these very, very tiny shifts in the position of the star. There are a couple of other methods which we can't quite do yet. One is atmospheric chemical analysis, and the hope is that we'll be able, that once the eternally plagued James Webb Space Telescope launches here this Halloween-ish, fingers crossed, it doesn't get delayed again for getting out of the launch pad, that James Webb will be able to actually look at the atmospheres of some of the planets that we've detected with Kepler and TESS. Another method is we also use detect planets using their radio emissions. The forming planets in particular are in a very infrared and radio wave rich environment, which makes them much easier to detect using radio wave astronomy than visual astronomy, which is what we might expect. There's just, because of so much dust around these forming stars, you wouldn't be able to see it with visible light in the first place. So the paper was wanting to ask if advanced alien life lived on other planets around us. We might not have detected this life yet, but assuming it's there, how many other planets or stars around Earth are in positions to where they could see Earth the way we can see the stars around other planets using methods like transit or radial velocity. So far, so good?
Yes.
So one problem that complicates answering this question is that everything orbiting the Milky Way is not moving is moving in the same direction for the most part, but they are moving. So stars closer to Earth, please excuse me for a second. So stars closer to Earth, if we're looking at them from Earth, they're going to be moving faster from our point of view, much like how a car is driving in front of you as you're trying to cross the street passes you much quickly than, say, an airplane passing above you 30,000 feet ahead. The plane is much farther away, so it's covering, even though the plane is going 600 miles an hour, it appears to move slower from your position than the car that just drove in front of you. Same basic principle here. So, did someone say something? No? Okay. So because of this general motion in the Milky Way galaxy, and the fact that our own solar system is moving, planets and stars will move in and out of a bubble of space where they could possibly detect us over time. And as I kind of mentioned, stars that are closer to us will experience, will move through this detection range much more quickly than stars much farther away. This particular paper was using data from Gaia, which is a space telescope that was launched by the European Space Agency. Excuse me. And Gaia's main purpose is to catalog very precisely the positions and motions of over 1 billion stars in our galaxy. So providing a lot of, some of the key characteristics of like stars that are both near Earth, but also where are they moving, so we can say, are they in this range of detection or not? For reasons that weren't talked about inside of the news article, mostly because they're kind of complicated. The researchers defined a bubble of space that's about 10,000 light years wide as their starting point for a search radius. Part of this was also driven by human life has only had meaningful civilization for the last 5,000 to 7,000 years. They could have gone back farther than that, just for other primordial life, but the speed of light is our enemy in this particular case. And using this bubble as a way to say what planets in the past, currently, and in the future are in positions to detect us, or to observe Earth in the ways we talked about. A little bit complicated to get through some of that. So within that, they then further narrowed it down to looking at about 325 light years around the sun to kind of tamp down on various time periods. This smaller range was chosen mostly because for two reasons. One, for limiting ourselves to planets that might be able to also detect our radio emissions, but also as a way to, if something of interest was, if we did find exoplanets, or when we, excuse me, not if, for many of these stars, which we do know will contain exoplanets, because they've already been cataloged by TESS and Earth, would potentially offer opportunities for follow-up studies to image the planets around these systems as follow-up targets for future research. Even within that range of about 300 light years, they were able to identify over 2,000 star systems that would potentially be able to detect Earth using the transit method, using just the transit method, which for 300 light years to have around 2,000 stars, especially because the Earth itself is not within a open cluster like some of our other companions, like some of the other objects we might be able to observe, is a fairly large number of stars, in my opinion, especially because we're in a very quiet region of our own galaxy. Of those, about 300 stars have lost the ability to image us visually in the last century. But they, again, they would still be able to detect us using radio velocity or transit. And about 300 more will move into range where they could image us over the next 5,000 years. Hopefully we're around, even 5,000 years from now. Continuing on, about 2/3 of the stars would be able to see a transit of an Earth-Sun transit that would last about 10 hours. So from their point of view, they would be able to detect a dip of light as the Earth moves across the surface of the sun from their point of view, that would result in a dimming of the sun that would last about 10 hours. And about 1/3 of those will spend the next 10,000 years in range where they can detect a transit of the Earth across the sun. And of the 2,000 stars that we said earlier, 200 of those are sun-like stars. So G-class main sequence dwarfs, much like the sun here. And about half of them are M-class red dwarfs, which is unsurprising because red dwarf stars are among the most common stars in the universe, making up about 70% of all known stars. Questions, comments?
Yeah, I don't think AM radio escapes the Earth very well, and FM, we've had that, what, 50, 60, 70 years. Did you run into anything about how far our detectable radio waves have gone around us?
There are a lot of studies regarding that topic. And yes, you do raise excellent points that some types of radio waves don't really work, but AM specifically doesn't reach through our own atmosphere as well, because it actually uses the ionosphere to bounce back to get as much range as AM does. But the general acceptance is that, at least from the way that SETI approaches their research when tackling that question, is they just make an assumption of about 120 years as a visual range for any radio emissions, because there's a lot of other factors that may also contribute to how quickly our own radio wave emissions taper off from the source, including passing through the heliopause, which is the outer envelope of material from our sun that currently Voyager 1 and Voyager 2 pass through within the last few years. So there's a lot of compounding factors that make giving a really, really precise answer of how much radio waves we've emitted are detectable a bit tricky to narrow down. So it's generally anywhere between 120 years as a more positive estimate to basically give a theoretical maximum, if that makes sense. Versus, if we just say, hey, we can only detect 70 light years, that's more of a minimum range. So they typically go with the higher number because, as we know that you can't have gotten any farther than that. So it gives a little bit more of an area to choose from when designing some of these studies.
So Connor, the article based it on our current technology and applied it to an alien or potential alien. Did they extend that to say somebody that's 1,000 years more advanced than we are, or maybe has an ability to be 100 times more sensitive than our instruments?
So you'll typically see papers like that not try to make those conclusions because it's impossible to say what sort of technologies they would even use. So for this paper, they omitted any of those details just because it helps keep their research a little bit more practical and easier to digest. Restarting people typically look at SETI sometimes as a bunch of quacks occasionally, even though they actually do some really interesting and impressive research. So starting to speculate about alien technology is a good way to get professional astronomers to not want to pay attention. So yeah. They typically avoid trying to make those comparisons outside of like speculative research, which this was not. So.
Okay, thank you. Makes sense.
Any other questions? Cool. Moving right along. So continuing our recent theme of planetary science, as we had moved through all of the planets through main presentation topics here, one for another over the last 6 to 7 months. One of the interesting things is that Jupiter and Saturn are actually quite warm. Prior to Voyager 1 and Voyager 2, it was expected that planets farther away from the sun will receive less light and less heat than planets that are closer. This is, a very simple thing to understand. If you're very close to a giant fireball or a fireplace while you're out camping and you want to cool off, you take a couple steps away from the fire and you're fine. So made a very simple thing to kind of say, hey, we expect this to be true. Interestingly enough, Voyager 1 and Voyager 2 showed that the gas giants, Jupiter and Saturn in particular, were actually much, much hotter than they should be. To give you kind of an idea of just how much hotter, Mars's surface temperature is about negative 120 degrees Celsius during the day. Jupiter's atmosphere near the equator is about 350 degrees Celsius, about 2 times hotter than the temperature in which you would normally use your oven. When it's expected that it should actually have been at around minus 110 Celsius, given that it's about 1 billion kilometers away from the sun. Tying in data from the Cassini probe during its grand finale series of orbits around Saturn near the end of the mission's life, and the Keck Observatory for collecting data from Jupiter, they actually found that the planet's massive aurora systems are one of the main components driving the heat. For those who might recall, Jupiter and Saturn have some of the largest auroras, well, not have some of the largest, they have the largest auroras in our solar system, with often these fields of auroras stretching out for multiple times the length of the Earth. You could have an aurora stretching tens of thousands of kilometers across the atmospheres of Saturn and Jupiter. Using this data, they were able to see that Jupiter and Saturn were hottest near the planet's aurora systems and cooler the farther away you get from these storms. Now, to make aurora, you need a couple of key ingredients. The first and foremost, you actually need an atmosphere. So planets like Mars or dwarf planets like Pluto, which have extremely thin atmospheres, or in Pluto's case is just too far away from the sun to make really any difference at all, don't have enough atmosphere to stimulate aurora activity because it's just too dense. It's almost the consistency of trying to breathe inside of a vacuum itself. So there's not enough air there or atmosphere to develop an aurora. You also need magnetic fields, and you also need a source of charged particles. We'll cover more about the charged particles here in a second. So on Earth, the solar wind is the main provider of the charged particles, which interact with our atmosphere and magnetic fields to produce the aurora that we see. The solar wind strikes the upper atmosphere, gets pulled in by the Earth's magnetic fields and directed towards the poles, where it bounces off of oxygen and nitrogen in our atmosphere and causes those gases to glow, the blues and greens that you'll commonly see in aurora pictures. On Jupiter, Saturn, the magnetic fields are powered by the two planets' very large liquid, and in Jupiter's case, we actually think metallic hydrogen core. So on Earth, our core is a solid, very hot chunk of nickel iron, which basically acts as a giant magnet. In Jupiter and Saturn's case, is because they're so large, they actually compress hydrogen itself down to a liquid or into a metal, and that metal acts as a superconductor, which generates the electromagnetic fields. Because these planets consist in large part of hydrogen. Their large cores are what make Jupiter's magnetic field the largest structure in the solar system. If you might have seen a picture, which I was unable to really find a convincing one, where the envelope for Jupiter's magnetic field extends from about Mars all the way out to Neptune. I think it goes well past Saturn. So the Jupiter's magnetic field is immensely huge. In fact, only some of the sun structures like the heliopods are larger. However, even with their extreme magnetic fields, both of these two planets are still too far for the solar winds to actually act as the source of charged particles like they do here on Earth. There's just not enough solar material or solar wind that reaches the planets to produce these aurora. Instead, the charged particles actually come from volcanism from the planet's moons. In Jupiter's case, it's supplied by volcanic activity from the moon Io, and in Saturn's case, it comes from cryovolcanism. That's volcanism generated by ice or ices that are ejected by Saturn's moon Enceladus. The injected material enters orbit around Jupiter and Saturn, and there, surprisingly, because it's getting dragged by the planet's own gravity, but not falling into the planet, there's actually both sunlight itself is sufficient to actually energize these volcanic particles. Which, I know I just said that there's not enough sunlight to make the aurora. That's because they are the sunlight particles themselves aren't the main thing causing them like they are on Earth. It's an indirect cause. A little bit of nuance there. Because of this difference in how the auroras are created, they actually glow in the ultraviolet range compared to the visible light on Earth. So you actually, even with our tech, if you were to try to go out and observe Jupiter and Saturn with your own telescope, you would never be able to see the aurora anyway, because they are in a frequency of light that our eyes cannot see without aid of computers. And in Jupiter's case, they also glow a little bit in the infrared light as well, which is kind of cool. So with that, I hope I actually, darn it, I think I'm missing a slide somewhere. I hope it didn't get out of order. But finishing up this, so on Jupiter, with its massive magnetic fields and the supply of charged particles supplied by Io, these get dragged down into the charged particles get dragged down onto the planet by Jupiter's magnetic fields, where they push up against the upper cloud layers on Jupiter, triggering drag forces, and through that make friction, which produces the immense amount of heat. So basically, someone took a fan of really hot air, and that fan is enough to raise Jupiter's temperature about 500 degrees Celsius from where we would have expected it to be, which is kind of crazy when you try to quantify just how much energy that gets produced just from friction of particles smaller than grains of sand rubbing into Jupiter's atmosphere, which is ridiculous when you try to quantify that. It's like, wow. Questions before we move on to the next one?
Yeah, Connor, when you talked about how Jupiter and Saturn were hot, it made me think of the studies that the Parker Solar Probe and some others are doing on the sun as to why the corona is so hot. And I was wondering if this was, well, of course, that's a star and these are planets, but it kind of sounds like this, maybe some of the same processes.
I think they've generally ruled out magnetism as the main thing. The I think it's the photosphere. No, that's the no, the corona region, which is this envelope around the sun, is I think they've ruled out magnetism as one of the key impactors for why the corona is on the border of about 1 million degrees temperature difference compared to the surface of the sun. It's just such a large difference that magnetism alone isn't enough to explain the difference. So it's an interesting question in general, and I'm not quite sure what all has been currently ruled out as contributors to that, to why the corona around the sun is so hot. But excellent question. Anyone else? Cool. Moving right along. So as the next topic, continuing with a new supernova subtype, which has been observed for the first time. So one of the first recorded supernovas, there was a couple that were detected earlier than this, was cataloged in the year 1054 by Chinese astronomers. There were 2 other supernovas that we know about that were also cataloged before this as well. Both of those were also recorded by Chinese astronomers, but focusing on 1054 specifically because it plays into the supernova subtype. The remnants of this supernova, called generally referred to as SN 1054, created what are now known to us as the Crab Nebula, or Messier 1. And until recently, was generally believed that Messier 1, which or the Crab Nebula, I'll bounce back and forth those 2 terms throughout this because it's just inconsistent, so I apologize. Were believed to be what's known as a type 2 supernova. There are several different varieties of supernova. There's actually another presentation that I did in November of 2019 to walk through all of this. If you want to, if you would like more of a primer on supernovas, let me know, and we can get you. I can send you emails that will get you access to the presentation so you can look it over. But in general, stars that are 8 solar masses and lower end up as white dwarfs, which is what's going to happen to our sun. And stars that are 10 solar masses or larger end up as supernovas. There are several, depending on the mass of the star, above the 10 mass threshold is the main characteristic that determines what type of supernova that star will actually turn into, or if eventually that star will turn into a black hole. Notice that there's actually a 2 mass gap between 8 and 10 solar masses there. So it's kind of, well, what happens between there? So in 1980, a Japanese astronomer called Kenichi Nomoto, there's a lot of, devised a new supernova subtype, which we hadn't really identified in observations before. So up until this point, it was just considered a hypothetical supernova type. We hadn't really seen it, so we couldn't really say it doesn't exist, but we also couldn't say it does exist. To kind of summarize this, because I couldn't really figure out a way to put it succinctly, but in an electron capture supernova, the star is not heavy enough to produce iron when its core collapses, to produce an iron core collapse supernova. This is what a type 2 supernova generally is. The star gets massive enough that it starts fusing carbon and heavier elements into iron within the star's core. And when stars produce iron through nuclear fusion, it's generally the death knell. Iron is a substance that takes more energy to fuse than the fusion reaction produces, so the star can't maintain balance and then explodes, usually within a few minutes of the first productions of iron in the core. But at the same time, these stars are not white enough to prevent the core from collapsing entirely. So they're really heavy stars, but not heavy enough. So instead, what happens is these stars stop the fusion process when their cores are mostly composed of oxygen, neon, and magnesium. In this scenario, the loose electrons bouncing around the core are grabbed by the neon and magnesium, which reduces the pressure in the core. Explaining this without going into some in the theoretical physics is really hard to do. So just kind of imagine that you had a lot of gas flying around, and then you suddenly confine it into a balloon using a magnet, and so the balloon got smaller, something like that. It's not a great way to explain it, but it's good enough for our causes. Because this pressure gets reduced, this causes the core to buckle under its own weight. And this results in a supernova. So during this process, the star will first eject the outer layers of its atmosphere, for lack of a better term. And then shortly after that first round of ejections, the star will go supernova. Once the star goes supernova, the shock front of the explosion will catch up to this first set of material that the star ejected and basically cause another reaction with that. So that, imagine you had something like, when you take a car going 100 miles an hour and it's going to strike a car going at 10 miles an hour, it's going to make a lot of energy in the form of a gigantic crash. This is the same thing here, where you have supernova material that's moving at tens of thousands kilometers per hour, or per second, I think, in most cases, colliding up against another set of gas and dust that's moving at thousands of kilometers per second. And that produces a whole series of interesting reactions and energy. So this collision of these two differing speeds of gas from the supernova increase the overall brightness. So it actually produces a supernova much brighter than you would get for a star of the size that it is. So it makes it difficult to sometimes tease out from brighter supernovas. So in order to actually trigger an electron capture supernova, you need a set of Goldilocks properties on these stars. So the stars need to have a lot of mass, but not too much mass. They need to lose a lot of that mass before they explode inside of and eject it as a cloud around the star. The star needs to have an unusual chemical composition, which unfortunately the paper didn't go into the phrase unusual and how they classified that. But going from the previous definition, you would probably expecting higher amounts of oxygen, neon, and magnesium than you would otherwise expect, when you might be expecting other elements like higher amounts of carbon and helium. So not quite sure on what they mean by unusual. The resulting supernova should be weak, which again wasn't really a term that they defined. And there should be little radioactive fallout. And the core should contain neutron-rich elements. So kind of explaining these last two, because you would think that this is a star, what's radioactive? So supernovas are responsible for producing, as I said, stars themselves will stop nuclear fusion when they produce iron. So the question then becomes, where do all elements heavier than iron come from? The answer is they come from the remnants of supernovas. So when they're saying there should be little radioactive fallout here, they're trying to say is that in the supernova remnant, which produced a lot of other heavier elements than iron as a result, that you would not expect to see a lot of heavier elements like lead and uranium and plutonium in the supernova remnant. but you would also expect that there to be other neutron-rich elements like gold and silver and other really heavy elements that aren't radioactive themselves. That's what they're trying to say. And I see that there are a couple of messages in the chat. Oh, those were direct messages. Okay, I will get to those in a second. So good so far. Kind of combining a lot of topics over some material that we've gone over in the past. Mouse, please click. So now that we have the signature to look for to identify these supernovas, the challenge then became actually finding one. So in March 2018, in NGC and the galaxy NGC 2146 in the constellation Camelopardalis, the supernova SN 2018 ZD was the first supernova that we've detected that met all of those conditions. You know, even though you're saying, hey, this is 2021, this thing happened almost 3.5 years ago now. It took a long time. After the supernova was detected, they did a lot of follow-up observations in order to basically try to narrow down what they were actually seeing with this particular supernova. Then for reasons that I can't explain how they decided to do this, they cross-referenced the data from 2018 ZD with the Crab Nebula. And there was a lot of similarities in the Crab Nebula between the Crab Nebula and this new supernova, which was suggesting that, in fact, the Crab Nebula was also an electron capture supernova and not a type 2, which is kind of interesting. In this particular case, we're saying, hey, we've had this expectation for a long time, and it might not be true, which happens a lot. Questions or comments? Okay. Moving on, this is the last topic of tonight before we wrap up. This one was the only one I actually found a really cool picture for, with that was actually published with the paper that was not behind a paywall. This one is detailing how magnetism contributes to the formation of planets around young stars. To give you an idea of what you're looking at here, the lightish blue areas around that you see in this picture are actually magnetic fields captured in the dust of a simulated star. This is a star from a simulation being run on a supercomputer. And the center is the area of the sun, of the forming sun, that they've just sort of removed to make it easier to see. And the tiny red dots you see all throughout this picture are planets that are forming around the star. So planets form out of the same material as their host stars. You have a lot of gas and dust that starts to collect into bigger and bigger rocks, and then eventually asteroids, and then eventually planetoids, and then eventually planets, and then, depending on where you're at, into rocky terrestrial planets like the Earth, or gas giants like Jupiter and Saturn. The primary means of this gathering of material to form planets is generally done by gravity. Larger and larger pieces of rock gathering, the smaller things around it. In addition to that, the light and radiation emitted by the star, by light from the forming star or the young star, is working to take all the gas that was close to the star as the star was forming, but not close enough that it became part of the star, and it's pushing all of that close in gas farther away. As this material moves out, it's going to reduce the amount of material close to the star to form big planets. Is the general theory, which is why you have these small rocky planets like Mercury, Venus, Earth, and Mars in the inner solar system, and you have these large gas giants in the outer solar system. For those that have paid, who are familiar with the planets that have been found by Kepler and by Kess, you know that this isn't quite always true, and that's kind of one of the things that's puzzling is when it comes to planetary formation, when you have giant planets, like the size of Jupiter, orbiting stars as close to orbiting their parent star closer than Mercury orbits the sun. So one of the things here is, how do these stars maintain enough material around them to form these really huge planets so close in? As this gas is getting pushed farther out, larger rocks, which are too heavy to be affected by the pressure from the star's light irradiation, typically remain where they are. Again, helping to contribute to the larger number of terrestrial planets close into the star than you would expect out in the star, out farther in the solar system reaches. Kind of a lot there to digest. Any questions? Okay. As one would expect, I had to touch on a second ago, excuse me. And most computer simulations we have of planetary formation, gas and dust is blown out too quickly to allow large gas giants to form. So there's been pieces in our own math that keep us from understanding exactly what we're seeing with Kepler and test data. That being said, excuse me, loose gas and ionizing radiation are easy ways to generate magnetic fields. Just because you have a lot of charged gas, basically a plasma, essentially, much like the sun, and plasmas are are electrically charged gases, and where you have electricity, you have magnetism, from the electromagnetic force, one of the four fundamental forces in the solar system and the universe. So there's a lot of overlapping there. So we know that these disks of material that form planets should be rich in magnetic fields. For a lot of reasons. So we know that this magnetism must be doing something to protect the planets, but for a lot of reasons, most of them just because it's really hard to do and getting enough computing power to do this. Simulating just all of general relativity and special relativity on its own is really, really hard to do for computers. You need a lot of processing power and a lot of time to create these simulations. Adding in magnetism increases that complexity by a lot, which is in part why some of our until here with this new work, most of our simulations of planetary formation never included magnetism in it, just because it's too difficult for computers to do. You would need millions of hours on a supercomputer of what can return CPU hours on a supercomputer in order to run the math to simulate even 15 seconds of time for planetary formation. And you're having to run these calculations for magnetism and gravity over particles of gas and dust, like you would try to animate sand blowing in the wind. It's a lot of work to try to move all of those sand particles around all together at the same time using very complicated math. So that was the that was the primary reason why we haven't had, magnetism included in simulations before. So now that we've actually started to be able to include magnetism in our simulations, this has led to some really interesting things. From these simulations, we've been able to see that magnetism helps out the planetary formation in 3 key ways. The magnetic fields shield gas and dust from the stellar winds, much like how our own magnetic field, the Earth's magnetic field, protects us from the solar winds. You can think of this as the same principle, just on much smaller levels around clumps of gas and dust around the stars as they form planets. But it also works to slow down the growth of the planets to prevent the creation of supermassive planets, like planets much larger than Jupiter, for example. At the same time, the magnetic fields act as a mixing agent, breaking up some clumps of gas and dust, and at other times collecting these collecting these gas clumps together. So both kind of like how you would take something in a pie mixer, and you're going to break up the flour so that it gets spread more uniformly, in much the same way. Once they've added these magnetism to their simulation, it tended to actually create more Moon and Neptune-sized planets and discouraged the formation of super Jupiters, which gets even more interesting. So there's still some pieces in this puzzle of how planets form that we're missing in our own simulations. And our primary limit here is just our ability and our technology to actually simulate all of the complex math that these simulations need to produce a result. Or also that, there's things that we don't understand in detail about planetary formation entirely that we haven't been able to detect yet because our own telescopes can't peer enough into these disks of forming planets to help guide us into what we're missing. So really cool to think about, where we might see next in terms of just trying to answer these questions of how exactly planets form, and kind of answering, from what we've seen in Kepler and test data, the structure of our own solar system is highly unusual. Our planets are in very circular orbits compared to a lot of the planets that we've detected using Kepler and TESS. So the question is, is our own solar system an oddball, even more than we thought for planetary solar systems? Or, there's also the possibility that Kepler and TESS, because of the way that they detect planets, are only detecting planets that, are in these eccentric orbits, which is also a very real possibility, And if you do want this presentation, I do have references to all the articles that, in some cases, use better words to explain what I could do here in the last 45 minutes hour, to go through all of this material, and definitely worth checking out if you're more interested in some of these topics. Thank you, everyone, for your time. Any questions now as we wrap up here? Oh man, I'm not a big fan of silence. Everyone still awake?
Well, I just came on, so I got the last 2 sentences, I'm afraid.
I'm sorry, Bernie. You want me to send you the recording once I get it up?
Yeah, I figured you'd be posting